Okay, let's take a look at this serial adder circuit. It's labeled serial adder, so we know that's what it is, but we'll go through our synchronous analysis process to analyze this circuit. Then we'll go through our synchronous design process to design a circuit with with shift registers, excuse me. So let's take a look here. We have shift register A, shift register B. We don't know how many bits there are in that shift register, so it could be any number of bits stored in that register. Then they are both feeding, one's feeding the X input, one's feeding the Y input of a full adder, and then we have our we have another D flip-flop that's storing the carry for a full adder. So if we look at what's happening here, we're going to start with all the registers reset. Now we don't show an asynchronous reset on these shift registers. So we're either going to have to shift in a bunch of zeros in order to get them to have an initial state of 0, or use this asynchronous clear also on the shift registers. But so the first thing we want to do is shift a number into register B. Here's register B here. So through this serial input, that's our only input to this circuit. Here we have a shift control that goes to both the shift registers. We have the clock that goes to both the shift registers, but we only have one place for data input, and this is this serial input here. So we'll shift a number into register B. As that happens, something's still going to get clocked into register A. What's going to get clocked into register A, if we follow that, that's the sum output from our full adder. So a 0 plus a 0 will be a 0. So as we're shifting a number into register B, a 0 will be shifted into register A. We must assume that both these shift registers have the same number of bits. So once we get the entire first number shifted into register B, then we'll start shifting the second number also into register B. And when we do that, we'll be adding B plus the 0 that was in A, and that will be shifted back into A. So we'll end up with, after we shift the second number into register B, we'll end up with the first number in register A. So then we'll have both our X and Y numbers that we're trying to add. So how do we add them? To add them, now they have them both sitting here at X and Y, so we need to continue to shift into register B. So as we continue to shift into register B, a third number will go into register B, but the sum of this original two numbers, A plus B or X plus Y, will end up in shift register A. And so that's how we'll end up with that addition. And then if we don't want to do if we don't want to add any more numbers, we could just shift 0 into that third number into register B. So that's where we'll end up with our finally with the sum of the two numbers in register A, and we'd have to get that information out of register A in order to use it. So what we also have here is this D flip-flop that's doing the carry. So as we're adding things in, if we're adding in a 1 plus a 1, the full adder will put a 1 here, and it also put a 1 here. So in the next cycle, we'll get that, because the only thing that's going to be shifted back into register A is the sum of 1, so we have to add the 1 in the next time. So this is acting like a little state machine, this flip-flop here. And then, of course, what we have here for our clock, we have our clock going into this flip-flop. This clock is gated with the shift control. So if we're not shifting into the registers, we're also not changing what our last state of this carry out was. So let's take a look at what that would look like, continue to analyze that. What would the timing diagram look like if we assume these two shift registers are just 4-bit registers? It will take 4 cycles to shift each number in. So if we're trying to add up 1010, or a binary 10 plus a binary 7, what will that look like? So our first cycle, we will get it'll take 4 cycles to get a number into 1, 2, 3, 4. Yeah, I guess I have them labeled up there. So the first thing that we're going to shift in, first we shift into register B our first number. So if that's our 0, 1, 1, 1, what was in register A, it was a 0, and what was in register B was a 0, so this is still going to just be 0, 0, 0, 0. And then for 4 more cycles, we'll shift in. Let's get that right. We'll shift in the 1, 0, 1, 0, and what gets shifted into register A then is our 0, 1, 1, 1. And then what we're going to do is end up with the addition of the two. And in register A, at this point it doesn't matter what we're shifting into register B, we can just shift zeros into there, but we're going to end up in register A is the sum of these two, right? So we'll end up with a 1, 0, sorry, 1, 0, and then 0, 0, because we'll just end up with a 1. So what's going on with Q and S there? Let's take a look at this completed timing diagram. I guess here I have shifting in the A first and then the 7. Then we end up with, then we'll shift 0 into register B. So A initially had a 0 in it. In the second 4 cycles, we shift the 10 in, and the second 4 cycles, we're shifting in the addition of these two. And so then you can analyze what's happening with your sum and with your carry due to this addition. So I'll let you copy down this timing diagram and see if you can verify, analyze that's in fact what's happening with S and C. The C, however, the next cycle is where it becomes the Q that's going to be the carry in. So see if you can't come up with the same result there. So pause the video so you can write that down, and then we'll continue. Okay, all right, so if we compare then our serial adder to our parallel adder, the serial adder with the ripple carry, that required 4 full adders, and we have to assume our A and B up here, we still had to have those coming from somewhere, so we still needed to have 2 4-bit registers for A and B, and then we need another register here to store our sum, whereas our full adder, our serial adder, we just needed 1 full adder. We still needed the 2 shift registers, so instead of being parallel load registers, they're shift registers. But if it's if it's 4 bits, then these are both 4-bit registers, similar to these 2 4-bit registers, A and B. And then we need an additional flip-flop here, and we end up storing our sum back into shift register A. So although it takes a lot more cycles to complete the addition with a serial adder, the hardware is significantly less. We only we really can compare the fact that we have 1/4 of the combinational circuits here, combinational circuitry in terms of full adders, and then instead of having another register to store the sum, we store that back into register A. So you compare that 4-bit register to this 1 D flip-flop that we have to store the state. So we saved a significant amount of hardware, and additionally we were able to, even though this is going to take, we saw it took 12 clock cycles to do the addition, whereas this we could do in 1 clock cycle, so it takes 1/12 of the clock cycles. This frequency of clock can be higher for a serial adder. All right, so that's analysis. Let's look at how we can design with a serial adder. So if we're designing with a serial adder, the design itself won't necessarily include the shift registers. We will assume that this block diagram that we're going to design with our sequential design procedure has as inputs X and Y numbers being shifted in from these 2 shift registers. So then we need an output sum, and then to design this, we'll let Q be the carry, because we know that, we know if we're going to need that carry for the next add, so we need that for our next state. So we'll call it Q, but it'll be our carry out. So to design that, our first step is to create a state diagram. So here I have the state diagram completed, where if we're in state 0, we can only have 2 states. We only need one carry out. If we're in state 0, our carry out or Q is a 0. If we're in state 1, our carry out or Q is equal to a 1. So that's, you know, like I think it's the Moore state machine there. But our sum, that's going to change based on the inputs, and that's what we just analyzed as well. So if we're in state 0, if our carry out is a 0, if our inputs are 0, then sum is 0, and we stay here because our carry out is going to still be 0. If we get a 0 and a 1, or a 1 and a 0, then our sum output will be a 1, but our carry out will still be a 0 because that's still just going to sum to 1. However, if our 2 inputs x and y being shifted in are 1, 1, then our sum is a 0, but our carry out needs to be a 1. So we'll shift over to this next state. You know, and so all these, remember on the transitions, that's what happens on this clock edge up here when we get a clock edge. And if our carry out, if we're in a state where the carry out was a 1 in the last state, that means our carry in is a 1 in this state. So now we're adding 1 plus 0 plus 1. Well, that's still 2. So our sum is 0 and our carry out's 1. And, you know, 1, 0, so 0, carry out 1. A 1, 1, that's going to give us a sum of 1, but still a carry out of 1. It's only if x and y are both 0, then our sum becomes 1. And excuse me, we go back to state 0 there. So from this state diagram, we want to make sure we have our key here. Our key is that our state is Q. On our transitions, we have x, y, and it wouldn't matter if it's yx or xy here, but we have x, y, and then slash s, we have our output s changing based on x and y. So it's if x and y are not stable before the clock edge, sum will not be stable before the clock edge. So that sum has to be sampled synchronously with the clock as well. So we can put that then into our next state table, so into, you know, loading up our next state table, our present state of 0, our present state of 1. We have the 2 inputs. So when we're in state 0, we have 4 different combinations of x, y, and what happens to our next state and what happens to our sum. So this looks a lot like our truth table for a full adder, because that's what it is. But then what we could do is we could say, well, instead of designing this with a full adder and a D flip-flop, we'll use our synchronous design procedure. And let's say we want to design it with a JK flip-flop. Well, then, you know, if we are in present state of 0, we want to go to next state of 0. Well, that means we can either reset or stay the same. So we get a 0x, and, you know, again, 0x, reset or stay the same, reset or stay the same. Or if we need to, if the inputs are 1, 1, then we're going to go to state 1, so that's either set or toggle. So we can put our 1x here. So then we can solve for our JK. We can do that, you know, we can use a Karnoff map if we want. You can go ahead and use a Karnoff map, but you'll find that your J is just, instead of just being equal to, instead of just circling the 1, and then it would have to be Q prime XY, we find that, you know, J, we could also circle this one down here, so that's just equal to XY, and our K is equal to X prime Y prime, and our sum here, we can see that looks like an exclusive OR there, so our sum is still equal to X exclusive OR Y exclusive ORed with our Q. Remember, that's our present state of Q, of course, not our next state of Q. So then from our JK flip-flop input equations and our output equation, we can create our logic diagram. And our logic diagram will include the shift registers. We included a shift control on this shift register as well. And then we have our inputs to our J and K and our output S. So we can do this with a JK flip-flop. Instead of using a full adder, we can use a JK flip-flop. We still need this exclusive OR like we need in a full adder, and then we just need an AND gate and a NOR gate. So if we compare that to what we analyzed earlier with the full adder, knowing that what our full adder was our two half adders and an OR gate, right? Excuse me. Then these two exclusive ORs using the associative property is replaced with a three input exclusive OR, and then here we have two AND gates and an OR, so we just need an AND gate and a NOR. So it's similar, but slightly different design, and we use a JK flip-flop instead of a D flip-flop. All right, so that was an example of analyzing and designing with shift registers using our sequential design process.